So a lemma, have you ever heard of a lemma? A lemma is a theorem. It's a little theorem. And you usually use lemmas to prove other stuff. So when you see lemma written in old books, it's a little theorem or proposition that you can prove, and it's usually used to prove other things. So here's the result. T dotted with T prime is equal to, it's got to be the number 0, right? The scalar 0, because when you take the dot product, you get a scalar. Okay, what does T equal? Unit tangent vector, or the unit vector in the direction of motion, right? It's r prime divided by the magnitude of r prime. And what we're saying is if you take T and dot it with its derivative, so I didn't put in the function notation, but it is T of T. Oftentimes we'll leave off the function notation, but it is a vector valued function here. It's a function of the parameter little t, lowercase t. It is T of T dotted with T prime of T. It will equal 0 every time. So how could we prove this? Well, let's start. Here's my little proof of my little theorem. Let's start with the fact that we know what T dotted with T is. What would that be? Dot product. What's the magnitude of T? It's a unit vector, so the magnitude is 1. And a vector dotted with itself is the magnitude of that vector squared. It's 1 squared, or just 1. Would everybody buy that? So this is because we know T dot T is a constant of 1, right? Now, all I have to do is take the derivative using the Calc 3 product rule, and I'll come up with that result in the lemma. So take a look. So we're going to do, working downward, I'm going to take the derivative. I'll use Leibniz notation, d dt. Now, this is lowercase t. We're assuming that the input is represented by lowercase t, right? d dt, and again, I'm leaving off the input because it makes less stuff to write down. So we're taking d dt of t dot t. And then we're going to do it to both sides of this statement. So we're going to take d dt of the constant 1 on the right side, just to make it clear what I'm doing. I'll do the right-hand side for you. It's 0. Wasn't that nice of me? What's the left-hand side look like? Okay, so the product rule, it looks the same as the product rule for Calc 1, doesn't it? So you could take you could think of it like this: the derivative of the first, if this guy's the first and it's the same, that guy's the second, but it's the same thing. You could take the derivative of the first, t prime, and dot it with the second, right? Plus the first times dotted, dot product times the derivative of the second. Isn't that one way to write the product rule? Yeah. But I mean, doesn't the dot product commute? So aren't these the same thing that you're adding together? You have one of them here, one of them here. How many do you have? So you have 2. I'm just going to write the order t prime. Oh wait, over here, up here I wrote it the other way. So let me do it. 2 times t dot t prime. Doesn't really matter what order you write it in, right? Equals 0. Is that the whole thing? Just divide both sides by 2 and you got it. Divide both sides by that 2 and you got it. Okay, that's it. Done. So what's the interpretation of this? What does this lemma tell us? Good. So T, I'm going to use the notation from geometry, is perpendicular to T prime. They're orthogonal vectors. That's another word we use for perpendicular, right? Okay, that's something we need to know for the next result, or the next batch of results. By the way, this little proof would work in general. So it generalizes to r dot r prime equaling 0 if r dot r is equal to just a constant. You can generalize it very easily. Because it doesn't really matter that it's 1 here, it just matters that it's a constant. So here's the definition that lemma is going to help us with. So definition n, and this is of t, right? These are functions of a parameter lowercase t. So when you say n, you normally mean like n of t. When you say t, unless the input is specified differently, you usually mean t of t, a function, a vector function. So n is defined as t prime divided by the magnitude of t prime. Okay, right away, when you have a vector divided by its magnitude, you know its length is what? 1. So why it's called a unit vector should be clear. But it's also called, it also has adjectives principal and normal, right? So n is the principal unit normal vector. All right, to show you what I mean, I have to draw you a little picture. So let's say this is a curve C generated by r of t, a vector valued function. And for some particular value of the parameter, you get a point, right, on the curve. If you let t equal a particular number, little t, not big T. We know, what do we know? We know that t will be 1 unit. Let's say the direction of motion looks like that. We know that t will be 1 unit long, tangent to the curve. We'll say, for the sake of argument, that that's 1 unit, and that looks more or less tangent to the curve. So if that guy's t, then there are 2 possible unit normal vectors. Do you see what they are? So if we stay at that point, then the idea is, okay, let me make a copy of t, so I keep the same length here. There we go. Okay. So let me just rotate the, you know, it's going to change the length anyway, so that was a waste of time. But let's say it's the same length as t, but now it's a normal vector, right? Or you can imagine that that's a right angle right here. We would not call this n. It's one possibility for n, right? Turns out we're going to learn today that n has to be the vector pointing the principal unit normal vector has to be the vector pointing the other way. So there are 2 possibilities, but it turns out that n, the real n, will be pointing kind of out of the concave side of the curve, I suppose, if it's in the plane. So this is going to be n. And we're going to see exactly why that one has to be n in a few minutes, but that's what we're talking about here. 2 possibilities for the unit normal vector. It happens to be this one. T and n are 1 unit long. N is perpendicular to t. That's what we know from the above lemma, right? So certainly from this definition, because it just involves t prime times the constant 1 over magnitude of t prime, certainly this vector is normal to t, is perpendicular to t. And so the only issue with the definition is why does it have to be this vector versus this one? There are 2 possibilities in the plane. Why is it the one in purple?